Oh, hey, didn't see you there, guys. Oh, sorry, just getting ready for Summerfest, you know? It's gonna be crazy. Whoa. Alright, so I'm gonna teach you all about refraction and reflection today. Alright, so it's chapter 22 in our book. I'll also be telling you about rainbows and how it's used with refraction of water droplets in the air. So, reflection and refraction happens when light traveling in one medium encounters a boundary leading into a second medium. The processes of reflection or refraction can occur. In reflection, part of the light encountering the second medium bounces off that medium. In refraction, the light passing in the second medium bends through an angle with respect to the normal to the boundary. Often both processes occur at the same time, with part of the light being reflected and part of it being refracted. We have to remember that light travels in a straight line path in a homogeneous medium until it encounters a boundary between two different materials. So, when a light ray traveling in a transparent medium encounters a boundary leading into a second medium, part of the incident ray is reflected back to the first medium. Something that happens like with reflection in like the real world would be something called red eye when you take a picture. The reason why this happens is a photographic flash. Red eye occurs when a photographic flash device is used and the flash unit is close to the camera lens. Light from the flash unit enters the eye and reflects back along its original path from the retina. This type of reflection back along the original direction is called retroflexion. If the flash unit and lens are close together, retroflected light can enter the lens. Most of the light reflected from the retina is red due to blood vessels at the back of the eye, giving the red effect in the photograph. Another way of reflection in the real world would be say you're driving along on a wet night, your headlights beaming onto the ground with the wet ground. That could be reflection. When light moves from a material in which its speed is high to a material in which its speed is lower, the angle of refraction is less than the angle of incidence. The refracted ray therefore bends towards the normal. If the ray moves from a material in which it travels slowly to a material in which it travels more rapidly, it's greater than the original angle. So the ray bends away from the normal, which is, so you have an angle going in, here's the normal right here. Make it a smaller angle going down, then it goes back to normal. What this does is it changes where the light comes out of the object. So you got a piece of glass right here. It will go in, the light will go in here, the angle will change for a second, and then it'll come out a different spot than when it came in. So instead of just going straight like this, it chops like this and then goes down like that. The equation we use for this would be speed of the light in a vacuum over the speed of the light in the medium. And that is equal to the index of refraction. While we say this, though, we have to know that when light changes from one medium to another, its frequency does not change. So from that, we know that the index of refraction in anything but vacuum depends on the wavelength of light. The dependence of the index of refraction on wavelength is called dispersion. Snell's law indicates that the angle of refraction made when light enters a material depends on the wavelength of the light. To understand the effects of dispersion on light, consider what happens when light strikes a prism. A ray of light of a single wavelength that is incident on the prism from the left emergence bent away from its original direction of travel by angle theta, called the angle of deviation. Now suppose a beam of white light is incident on the prism. Because of dispersion, the different colors refract through different angles of deviation, and the rays that emerge from the second face of the prism spread out in series of color known as visible spectrum. That's all the colors going from red, orange, yellow, green, blue to violet. Violet light deviates the most and red at the least. The remaining colors in the visible spectrum fall between these extremes. But we found that all hot, low-pressure gases emit their own characteristic spectra. So one use of a spectrometer is to identify gases. Like sodium emits only 2 wavelengths in the visual spectrum, 2 closely spaced yellow lines. On the other hand, mercury vapor has its own characteristic spectrum, consisting of 4 prominent wavelengths: orange, green, blue, and violet lines. The thing we think of, like in nature, that is most common would be the rainbow. It's often seen by an observer positioned between the sun and a rain shower. What happens is the light is reflected and returned to the front surface, where it again undergoes refraction as it moves from water into the air. The rays leave the drop so that the angle between the incident white light and the returning violet ray is 40 degrees. The angle between the white light and the returning red ray is 42 degrees. This small angular difference between the returning rays causes the rainbow, basically. If a raindrop high in the sky is being observed, the red light returning from the drop can reach the observer because it is deviated the most, but the violet light passes over the observer because it is deviated the least. Hence, the observer sees this drop as being red. Similarly, a drop lower in the sky would direct violet light towards the observer and appear to be violet. And something other crazy that you can see, it's pretty rare, is called a fire rainbow. And they usually happen during the summer, and they're actually called, in real life, or the scientific term for them is called a circumhorizontal arc. And it can only occur when the sun has risen higher than 58 degrees in the sky. People at mid-latitudes have the best chance of seeing this phenomenon. For example, it's like 5 to 10 times greater to see this happen in Los Angeles than it is in London. Other than the position of the sun, other things that lead to this circumhorizontal arc is cirrus clouds. Those are the ones that are thin, wispy clouds that occur at high altitudes. Because this temperature is so low where the clouds exist, they're made of ice crystals. After the sun is higher than 58 degrees, the light refracted through the plate-like crystals, which act like prisms and create the rainbow. These clouds are like really cool looking, by the way. Another place you can see a rainbow is right over a gym box in Clash of Clans. I mean, no one knows. Maybe that's where the Lucky Charms goes. It's crazy. You get 25 gems just for that rainbow. Amazing. Alright, that's it. I hope I can give you all some good insight on reflection and refraction and how they're used to see like rainbows, fire rainbows, red eye, and just any light reflected by any sort of water on the ground during the nighttime or anything. Thanks for listening. Go H-Time, throw